not be coming through well. Hello, everybody. I've decided to enact the best kind of social distancing and put myself into outer space. So the next couple of lectures will be from my cockpit here of my spaceship. And we might as well go ahead and get started now. We've wasted enough time. We're going to talk about linear systems today, okay? And the great thing about really diving into linear systems is these are particular types of systems that we can actually do a lot of stuff with. So we're going to start off with some definitions here. Capital A is going to be a matrix A, which we will call our coefficient matrix. And so it's 2 by 2, 2 rows and 2 columns, filled with usually constants like A, B, C, D there. Those are number values or the whatnot. Y is a vector, so you see the little arrow above it, okay? And this is my state vector, and so it has my 2 state variables, because remember we're dealing with a system, x and y, and these are all functions of time, right there. So if I look at what is A times y, so what is the matrix times the vector y, I get a new vector, ax plus by, and cx plus dy, and I could write my differential equation then, the derivative of my state vector with respect to time is going to equal A times y. If you can write your differential equation system in this form, then it is linear. Simple as that, right? And specifically, it's the kind of linear that we are going to be dealing with. All right. Some of you may not be familiar with matrix and vector and multiplication and the whatnot. If you're not, I do suggest that like you kind of just look it up online and try to refresh it. But I'll also try to do a little bit here. I can't really spend a whole bunch of time on it. But basically what you do is you take like the 2 elements of the first row of the matrix and you multiply them by the 2 elements in the first column of the vector to get your first element of the next vector and so on. Match those colors, okay? So what we've got right here is we've got all of our definitions written down. The way that we are more comfortable seeing this, that we've seen it before, would be dx dt equals ax plus by, and dy dt equals cx plus dy. Okay, so these are all like, these are just similar ways to represent the exact same thing. We want to get comfortable with being able to deal with either of them. But what's gnarly about this is, as of right now, we don't know how to solve such equations, and that's kind of what I want to get into. Right? But the easiest thing to do when you don't know what to solve is to instead maybe think about just equilibrium. If I can't know general solutions, maybe I know one particular point where we don't have any motion. So I'm looking for a vector y star such that when I take A and multiply by y star, I get the 0 vector. Okay? And so what this means is that both x star and y star, we have to choose a particular pair there so that both values, dx dt and dy dt, are 0 at the exact same time. Otherwise, you could have x not changing, but y is still changing. We're not at equilibrium. So to do that, I'm going to plug in what I have for A, and then this x star, y star business, and it gives me a system of equations. 2 equations, 2 unknowns, x star, y star, and we should be able to solve this because they're nice and linear, okay? One solution that always exists, which is the simple or the trivial solution, is when both x star and y star are equal to 0. We can see right there, sure, that just solves that, no problem. Okay. What is a natural question here is then to ask, well, under what conditions do I have the non-trivials? All right, and for that, well, I guess what you can do is take your first equation and solve it for x star, and you get negative b over a y star. That seems great. Now, what you would normally do is you would take that and you would plug that bit of information into the second equation to get another expression. All right, so in this case, we're going to get c times that negative b over a y star because we're plugging that in for x star, plus dy star equals 0. Okay, if you just do a little bit of factoring right there, you know that you get like 2 basically possibilities, right? So just to give myself a little bit more room, c times negative b over a y star plus dy star equals 0. Okay, you factor that out and you're going to get either that y star equals 0, which is our trivial solution, we know that, or, and the other one here is if you take all those coefficients and you basically just do a little bit of algebra to them, we require that AD minus BC should be equal to 0. Now what's important there is that's given in our system, so it's not something we're free to choose, it just so happens. that if this is equal to 0, then we have a non-trivial, non-zero solution, right? And again, if y star equals 0, we look back up in our doohickey right here, our key, basically, you get the x star equals 0, okay? Now, AD minus BC, for those of you who have taken linear algebra, is a familiar quantity. But that basically, that equaling 0, the determinant of that A matrix equals 0, means that we would have a non-simple or non-trivial solution. And in fact, what you can show is that you would basically have like an infinite number of solutions. You'd have a line of them, okay? And so to kind of show that little bit here, okay, if AD minus BC equals 0, then this system right here, what you argue is redundant. And what that means is there's no information contained in the second equation that is not in the first equation. You'd be solving basically one equation with two unknowns. And what we should remember from like high school algebra is that means you have a line of solutions. And my line would be in the form of x equals negative b over ay, or if you're just more comfortable, y equals negative a over bx. And so that's a straight line that passes through the origin. And so you can see that even if you have an infinite number of solutions, the trivial solution is still in there, okay? And another way to kind of show that this is redundant, all right, if AD minus BC equals 0, then AD equals BC. And so I can just sort of divide out by some clever way, because I know what I want to look for, that D divided by C equals B over A, okay? Which again means that A over B is the same as C over D. But if I solve my second equation now instead of the first one, you would get x equals negative d over cy, which is the exact same information up here. So yeah, they're both telling the exact same story, just in different ways. Okay? So the moral of that story here is that if the determinant of A is not the same as 0, then your only solution to the equation, or your only equilibrium, excuse me, is the trivial equilibrium, the origin of the xy plane, that one point right there in the middle, okay? And that's really useful, basically, to work off of. If you have a line of equilibrium, we actually don't know how to deal with equilibria that are infinitely close to one another. We haven't bothered to deal with situations like that yet. We will in the future, okay? There's just one more point that I want to be able to make about linear systems, and it really has to do with like all this linearity principle that we've been building for every single one, okay? So if you happen to have two actual time-dependent solutions of a linear system, then you can take the linear combination of those two solutions, and that's your general solution. So it's the exact same thing that we've been dealing with before. So if y1 and y2 are solutions to my vector matrix form, then k1 y1 plus k2 y2 is the general solution. And that way that you know you have them all, okay? Thank you guys. This is pretty much all there is to it as far as introducing linear systems. We will go over a lot more detail of specific things as we progress, okay? I guess that's it. Thanks for tuning in. Where's the stop recording button?